Welcome. Welcome to a presentation of Global Process Control, made at a European AEC APC conference in Dresden, organized in Germany by semiconductor industry. This talk comes from collaboration between Renault and GPC System companies. I am going to talk about monitoring methods and tools to reduce variability in industrial processes. These methods and tools, developed by GPC System, are in operation at major industrial companies. I shall illustrate them with an example from Renault car factories. I'll start with a few facts about the assembly lines at Renault, then I'll present the GPC multivariate analysis technology and its application to the reduction of variability of cars' bodies. A Renault assembly line puts the various parts of a body together. Each body is supported along the line by a frame called pallet. At the end of the line, laser robots take monitoring measurements on each assembled body. The example I give makes use of data on 3,000 bodies collected over one short week. On each body, 43 measurements were available. They correspond to the gap between the theoretical position of selected points and their actual position in the 3D space. In this context, the purpose of Renault is twofold. First, to prevent and reduce non-conformity of the car bodies. Second, more generally, to reduce variability of the geometrical characteristics of the bodies. This is pursued by two means: directly, on the bodies; indirectly, on the pallets that support the bodies, because a distortion of a pallet can be a cause for systematic distortion of the bodies. Let me, now, introduce the GPC multivariate methodology, in use on this assembly line. I will explain it, using the most simple example, a two-dimensions example. The measured variables x1 and x2 follow each a Gaussian distribution, as usually admitted, under the commonly used SPC methodology, the statistical process control methodology. Green crosses represent observations under the usual, good functioning, of the system. The green dot is their average, the red dot is the target. As shown here, the green crosses are maintained in a region presenting an ellipse shape. It's what is commonly observed on real data, and what is stated by the probability theory for the two-dimensional Gaussian distribution model. GPC multivariate methodology determines an acceptance domain based on the accepted probability of false alarm, named alpha. This domain has the shape of an ellipse, as shown. Probability theory confirms common sense. This shape is optimal. For SPC, the usual value taken for alpha is 0.27%. That corresponds to the usual definition of the control limits by mean, plus or minus 3 sigma. Observations: the blue stars that fall outside this ellipse are the sign that the system is perturbed. For SPC, an observed point, x1, x2, is accepted if x1 and x2 lie in their respective control interval that are defined by their Shewhart control limits, LCL, and UCL. For each variable x, the limits, LCL, and UCL, are defined from the mean, the standard deviation, and the chosen probability of false alarm, alpha. So, in this two dimensions space, the domain of accepted points is a rectangle. Here, the red rectangle. But, probability theory says that the probability to be outside the red rectangle can reach up to 2 alpha. For the same reason, when you monitor 50 variables with SPC tools, you are confronted to a probability of false alarm that can be 50 times the alpha that you use on each control chart for Shewhart's limits definition. So, you may be alerted very often, losing much time in trying to investigate where the problem is, while no perturbation has occurred. In the industrial practice, this can lead to mistrust SPC, or to reduce drastically the number of variables used for controlling the observed system. That both behaviors raise the chance of non-detection of real problems. On the other side, GPC masters the false alarm to the chosen alpha value, even for hundreds of variables. By comparing the GPC acceptance ellipse with the acceptance rectangle of SPC, one observes the importance of non-detection areas, under SPC. The greater is the correlation between x1 and x2, the flatter is the ellipse, and the wider is the non-detection area. In order to decide when an observation point is inside the ellipse, we use of the T2 distance from the center of the ellipse. The T2 distance is calculated from the correlation matrix of the x variables. The T2 distance is such that all points on the ellipse have the same T2 value, while points outside the ellipse have higher T2. This T2 chart, built using the GPC scans software, illustrates the separation between correct and not correct functioning of the system. This control chart is based on the actual 43 measurements taken on each car body. The T2 value is the distance of each observation point from the center of the acceptance ellipsoid in the 43D space. In 3 dimensions space, the ellipse that we have drawn in 2 dimensions take the shape of a rugby ball. For higher dimension than 2, this shape is called ellipsoid. The control limit is defined by the probability law of T2, and the value of the accepted probability of false alarm, alpha. The dataset contains both under control and out of control observations. The ellipsoid, by definition, is based only on under control observations. But under control observations are not known a priori among the initial dataset. In order to overcome that objection, the method makes use of an iterative algorithm, rather complex, for building that partition and defines a suitable ellipsoid. A distinctive feature of GPC methodology is its capacity to identify perturbations of the process. The identification is based on the following principles. Principle 1, for a given cause, out-of-control observations escape from the ellipse in a precise direction. Principle 2, this direction is typical of this cause of perturbation, it characterizes the perturbation. These principles derive from a mathematical model, which closely fits most industrial measurements. Let us examine now the pertinence of GPC model in real life, in the context of our data collected in a Renault car factory. Remember that under control points are green. You can see that their group has the shape of an ellipse, as announced previously. Our interest here is on the classification of out-of-control bodies. We have identified 16 groups of out-of-control observations that correspond to 16 different causes of perturbation. These 2-dimensional views of the 43-dimension space of measurements show the behavior of different anomalies. Observations belonging to the same anomaly group are identified with a common symbol, red triangle, yellow square and so on. As announced, same symbols are organized along straight lines, as for anomaly number 1 in blue, anomaly number 2 in red, and so on. In order to help industry technicians identify the cause of a detected perturbation, GPC proposes them tools to answer the following questions quickly and easily. Which variables are perturbed? When does the anomaly appear? How is perturbed each variable? How severe is the perturbation? The tools of GPC are designed to guide the user through the examination of most relevant charts. Generally, these charts are obtained with only one mouse click. These GPC selected charts are easily interpreted by non-statistician, by industry technicians. Let's see that on our car bodies. This is the already seen 2D graph, showing anomaly number 2. With one mouse click on a red triangle, GPC yields the so-called anomaly signature. It is a chart where the 4 most sensitive variables are brought to evidence. Physically, on the car body, what does this mean? One click produces the body synopsis, where the anomaly signature is geometrically located. So, for anomaly number 2, the problem lies on the front left side of the body. The directions of the deformation are shown on the car picture. A technician of the assembly line has got already precise indications to identify the origin of the problem. The most affected variable is named 1Z. One click on its sensibility bar shows its control chart. On this chart, all the 3000 observations are represented. From the red triangles that represent car bodies affected by the anomaly number 2, we see that 1. Only a few consecutive bodies have been affected. 2. This was temporary, at the beginning of the observation week. 3. The perturbation had a severe impact. On this chart, all red points lay outside the upper specification limits, USL. That signifies that car bodies affected by the anomaly number 2 are all non-conform. This information enables industry technician to identify now, precisely, the technical cause of the perturbation. Let's now examine anomaly number 3. On the 2D view, this anomaly is identified as a set of yellow points. One click on the yellow point gives us the signature of this anomaly. On this chart, it appears that only one variable is affected by this anomaly, namely 18Z. The problem lies on the rear left part of the body. One body point is lowered. This point is close to a contact point of the supporting pallet. The control chart of the concerned variable, 18Z, shows that 1. The perturbation bears on isolated bodies in the assembly flow. 2. It happens throughout the observation period. 3. It produces non-conform bodies. How to identify the precise technical cause so as to decide on corrective action? In this case, we use a GPC tool that colors observations according to selected variables. Initially, dots are shaped and colored by the anomaly number. With 2 clicks on the mouse, the colors show which of the 100 pallets was supporting each car body. This newly colored graph immediately confirms what one could guess: anomaly number 3 is caused by a defect on pallet number 73. We have seen so far how the analysis of out-of-control observations enables reducing product variability. Now, we shall move to what can be done for reducing under-control variability. A cause of variability can be discrete or continuous. Let's start with the continuous case. Such a continuous cause adds to the measured variable a continuous time function. This yields a serpentine control chart. The GPC scan software uses the ratio sigma long over sigma short to recognize variables subject to such perturbations. One click produces the control chart of any such variable in order to better investigate the phenomenon. It is also possible to identify causes of continuous perturbation that are common to several measurement variables. For this purpose, one examines, for under-control observations, the principal components, or the principal variables selected by the principal variable analysis, PVA. PVA is also a specific tool of GPC technology. There is no place here for giving further details on these methods. Let's see, now, a few examples of discrete variability sources. Merging production flows from parallel equipment is often a source of discrete variability. Here, the outputs of parallel equipment, A1, A2, A3, are merged, and, if they are not all identically tuned, this will increase the standard deviations of characteristics of the outproducts. It is the same for raw material, coming in different batches. And, for ill-equilibrated rotating platform, that are often in use in automotive industry. In plastics industry, and in metallurgy, we often have variability problems caused by multi-imprints mold. In each case, production systems can take several different states. Each state generates an ellipse, whose center is slightly apart from the other centers. To identify among such situations, we examine the first PCA components of the under-control observations data. This is a way to focus on discrete causes having a strong impact on measurement variability. For our car bodies, this new viewpoint reveals that the cloud of points that should appear as an homogeneous ellipse is actually shaped in 2 distinct clouds. This is the sign of a discrete variability source, which presents two states. Let's try to characterize these two groups. GPC scan allows us to create a two-values variable, typical of the belonging to one or the other group. This is achieved simply by enlisting the body's observations that the user judges belonging to each group. Now, we can assign different colors to observations from one or the other group. The lower left graph shows the difference between averages of the two groups for all 43 measurement variables. Variables are ranked according to this difference. The lower right graph is the control chart of the most impacted variable. It illustrates how observations from the two groups are distributed along the time axis. Such charts help industry specialists to find the technical cause. Now, I turn to the issue of pallets as a source of variability for car bodies. Renault wished this source to be precisely investigated. Renault specialists have selected on the car body 8 measures of points close to the contact with the pallet. A pallet measurement is defined as the average of measurements of all bodies supported by this pallet. Irregular bodies are eliminated from the calculation of this average per pallet. The algorithm used earlier to separate under control from out of control observations is now applied to the pallet's measurements that are calculated from bodies data. The result has detected 4 outlying pallets that may be defective. Among them is pallet number 73 that was already noticed as cause of anomaly 3. On the pallet's synopsis, GPC gives indications on the tuning required on the 4 defective pallets. What are the main points to remember about these data on Renault car bodies? They are numerous, 3,000 observations of 43 variables. They generate too many alerts with SPC. They comply with the multivariate GPC model that was presented at the beginning of the talk. We have seen also that GPC tools are efficient on various concerns of process monitoring and optimization. They master false alarms. They can detect precociously accidental perturbations and lead rapidly to technical interpretation. They are able to identify ordinary variability sources. Furthermore, with these tools, we have been able to select the pallets that must be tuned without any measurements taken on them. Finally, lots of relevant views on the data are obtained by only one click. That's why Renault decided to use GPC for daily monitoring on 7 European sites. GPC model is the base of others' useful functionalities for improving process quality and productivity. We don't have the opportunity to use them on our car bodies example. Such useful functionalities are process tuning, operating point optimization, variables selection for reducing global variability, or adjusting process. Real-time monitoring. Another function which is useful for plastic injection, or for painting robots, could be interesting in semiconductor industry, the optimized construction of indicators from a curve obtained by sampling a time variable during a product cycle. Thank you for your attention. Any questions?